Okay, hello everyone. So in this part 3, we'll describe about monochromatic light in phase at some distance away in vacuum to describe constructive interference and destructive interference. Okay, so a quick recap from where we stopped from part 2, all right? Basically, when there are two light sources, and if you want to find the path difference towards a certain point, so let's take for instance, right, point A. So what's the path difference between S1 and S2? So we can count, right? S2 takes 1, 2, 3, 4, 5, 6, 7, 8 lambda, whereas S1 took 1, 2, 3, 4, 5, 6, 7 lambda to reach point A. So we know that S2 travel longer. So S2 took 8 lambda, S1 took 7 lambda. So the path difference is 1 lambda. Okay, if we take a different point, again, we can count the path difference. In this case, we can see S1 travels longer. So S1 took 6 lambda, S2 took 3 lambda. So the path difference is 3 lambda. So we can generalize it, all right, that in the case when we see constructive interference, the path difference must be a whole number lambda, or what we call it as m lambda. Okay, this here is where a crest meets a crest, so it is constructive. A crest meets a crest, it is constructive. Okay, let's take for instance point C. So point C is a region where we'll see destructive interference because it's a crest meeting a throw. So we can see that S2 has traveled longer in comparison to S1. So the path difference will be 3.5 lambda. To point D, the path difference is 1.5 lambda. And again, at point D, it is destructive interference because it's a crest from S2 meeting with a throw from S1. So you can generalize it that in the case for destructive interference, the path difference must be m plus half lambda. And m, right, is an integer value. It takes the value of 0, 1, 2, and so on. Okay, so what is the path difference to point E? Would you see it as constructive or destructive? At point E is a throw from S1, and it is also a throw from S2. So when a throw meets a throw, it is constructive interference. So when you calculate the path difference, then it will be m lambda. All right. Okay, so let's recap. For two monochromatic sources in phase, the wave at a point some distance away in vacuum can be described by constructive as well as destructive interference. So constructive interference is when the path difference is m lambda, and destructive interference is when the path difference is m plus half lambda. So where m is an integer and lambda here is the wavelength of the wave. Okay, the next thing is describe how diffraction of light by slits in a two-slit interference apparatus allows light to overlap and hence interfere. And sketch graph of the intensity distribution of two slits interference of monochromatic light. So consider only cases where the slit separation is much greater than the width of the slit. Okay, this here is basically describing Young's double slit. So we start with two sources. The only difference is now in Young's double slit, he used a monochromatic light source. And this monochromatic light source is passed through, first of all, a single slit. Because a monochromatic light source is not a coherent light source. So to make the light source, right, it comes out from S1 and S2 coherent, you need a single slit. Okay, these two light sources, right, that comes out are coherent. That means they maintain a constant phase relationship. Okay, why are they coherent? Is because, right, you see, both of these wave origins from the same source. Can you see this crest? So when this crest passes through S1, it's the same part of the crest that passes through S2 simultaneously. So when these two waves, when this crest passes through S1 and S2, they diffract for the second time. So these two will be coherent. So at some distance away, right, what Young's subtopic experiment describes is basically an interference pattern. So the interference pattern will be made up of constructive, which is a bright spot, and a dark spot, which describes destructive. So you get constructive, destructive, constructive, destructive. So an interference pattern that you see. Okay, this line, this dotted line represents the perpendicular bisector, right? It's bisected because it divides S1 and S2 right into half. And what we see on the perpendicular bisector is basically constructive interference because it's a bright spot, then followed by a dark spot, and a bright spot, and a dark spot. So the question is, why do we see constructive interference here at the perpendicular bisector? Okay, let's describe, all right? First of all, what do we see on the screen, all right? Basically, this is the central maximum, all right? It's known as central maximum, or it's also known as the zero order constructive interference. This here is known as the first order constructive, the second order constructive, the third order constructive. It is similar like your coordinate axis along the y direction, right? This is your 0, then this is 1, 2, 3, 4, and so on. Right? So this is not -1, but it's actually known as the first order constructive, second order constructive, third order constructive. For destructive, right, there's no zero order destructive, right? Because like coordinate axis, there's only 1, 0. So this is the zero order, which is already taken up by constructive interference. So this has to be first order destructive, and this is known as your first order destructive, second order destructive, third order destructive, and so on. So coming back to the question, all right, why do we see constructive interference at the perpendicular bisector? Okay, the light source that comes out from S1 has to travel along the path that's drawn here to reach this perpendicular bisector on the screen, all right? And the light source that comes out from S2 has to travel through this line to reach this part on the screen. So since this is constructive interference, that means we know the path difference must be equals to m lambda. So the question is, what is m? Right? So constructive interference, you see, we use m lambda. But what is m? So m, right, is always an integer value. So our m always starts with 0, 1, 2, 3. So this is the first value, or central. That's the first constructive that I see. So the first constructive that I see, I have to substitute m equals to 0. So in this case, 0 times lambda gives me 0. So what does it mean? That means my path difference for the first order, or for my central maximum, or my zero order maximum, is when the path difference is equals to 0. So now we can see that it makes sense because the distance that S1 has to travel to this point on the screen is the same as the distance that the light source S2 has to travel from its origin towards the screen. So this distance is the same, so therefore the path difference is 0. Okay, now let's take a different point. All right, this point on the screen. So this here is known as my third order constructive interference. So constructive interference, that means the path difference must be m lambda. But what is m? So for the central maximum, first, second, third order maximum, that means my m will be equals to 3. So for my third order maximum, my m will be 3 lambda. So for constructive interference, it's rather straightforward. M is always an integer. It starts from 0, 1, 2, 3. So since constructive interference starts with 0 order, first order, third order, and so on, right? So if I want to describe the third order constructive interference, my m equals to 3. So if I want to describe the sixth order constructive, m will be 6. So I just substitute 6 lambda to calculate the path difference. Okay, now let's describe destructive indifference. Okay, this is a dark spot. So basically, this is disruptive indifference. So to describe the path difference, that means destructive indifference, the path difference will be m plus half lambda. Right? That's what I write. This is my path difference. But the question is, what is m? So let's look at this. This is my first order destructive, second order destructive. This is my third order destructive. So my m starts with zero order destructive, second order destructive, third order destructive. So for my third order destructive, I substitute m equals to 2. So it's actually 2.5 lambda. So what does this mean, all right? That means we can see that for the light to strike this part on the screen, all right, we can see that S2 has to travel longer as compared to S1. Can you say that? So the question is, how much longer must it travel in comparison to S1 for it to strike this part on the screen? That means S2 has to travel 2.5 lambda longer as compared to the light source from S1. So that's why they interfere destructively at this point on the screen. Okay, let's look at the different point here. So this is known as my first order destructive interference. So my first order destructive interference starts with m equals to the first value, which is 0. So I substitute equals to m plus half lambda. I substitute m equals to 0. So the path difference will be 0.5 lambda. So in other words, S2 has to travel half a lambda longer as compared to S1 to reach this point on the screen. So since there's a path difference of 0.5 lambda, you will see destructive interference. So for destructive interference, right, we always start with the first order destructive, second order destructive, third order destructive. So to describe the third order destructive, m will be 2. To describe the 100th order destructive interference, m will be 99. So that's why we substitute into m. So for destructive interference, it's not so clear-cut as constructive interference, right? The reason is because of how we classify the patterns that we see on the screen for destructive interference. We start with the first order destructive, second order destructive, third order destructive, but m starts with an integer. It starts with 0, 1, 2, 3. Okay, next is use a geometrical construction to identify locations of maximum and minimum amplitude due to interference of light from two wave sources of the same frequency. Then use constructive and destructive interference pattern to explain the maximum and minimum amplitudes and explain the bright fringes of two slit interference pattern using constructive and the dark fringe using destructive interference. So coming back to this, right, we want to perform geometrical construction to describe why we see constructive or destructive at certain parts on the screen. So I'm going to perform for constructive interference. So in order for us to explain why this part is constructive interference is because the light source that comes out from S1 has to travel along this line, right, to reach this point on the screen, point Q. Whereas the light source from S2, when it comes out, it diffracts and it has to travel along this line to reach this point on the screen. So from here, right, we can see that light source S2 has to travel longer in comparison to light source S1. So the question is how much longer? So you can perform geometrical construction, right? So if I draw a line such that S1Q is the same as PQ, right? So you can isosceles triangle, that is S1Q is the same as PQ. So from this triangle, we can see that, oh, S2 has to travel longer. How much longer? Is this much longer in comparison to light source S1? So we call this as the path difference. The path difference is actually S2P distance, right? Can you see that S2P is this distance? Okay, so let's analyze S2P. If I draw a line from the perpendicular bisector to the point on the screen. All right, this point Q, this is the line from the perpendicular bisector to the Q. So if I label this angle as angle theta, I can prove that this angle will also be angle theta. So how do I prove that? Let's look at this yellow triangle. All right, if I draw it bigger, this is your yellow triangle. So if this is angle theta, this angle will also be angle theta. This is 90 degrees. So if this 90 degrees from geometry, we know that this angle will be 90 minus theta. Because the total angle when we add up for a triangle will always be 180 degrees. Okay, next, let's look at this pink triangle. So this is the pink triangle here, right? So this is the pink triangle. So this is 90 degrees. This is 90 minus theta. So if it's 90 degrees, so therefore this angle will be angle theta as well. Right? So this angle theta. So if we measure the angle from the perpendicular bisector to the point on the screen, if we can measure this angle theta, we know that from geometry, this angle will also be angle theta. So now we can use trigonometry. What is sine theta? Sine theta will be opposite. So the opposite is 3, this distance as to b, divided by the hypotenuse. So the hypotenuse is actually the distance between S1 and S2. So that's what I get. Using trigonometry, sine theta is actually S2p divided by S1, S2. But what is S2p? It's my path difference. Can you see that? Remember just now, this is known as my path difference. And if I label S1 and S2 as D, right? If I label it as D, so I can say that sine theta is actually S2p divided by D. So S2p is known as my path difference. And my path difference is actually D sine theta. So D is the separation between the two slits, all right? S1 and S2. And theta is the angle that you make if you draw a line from the perpendicular bisector to the point on the screen. So this is the angle from the perpendicular bisector line to this line, all right, from the perpendicular bisector to the point on the screen, which actually you can measure right in the experiment. You use an experiment. When you conduct an experiment, you're actually measuring this angle theta. So in other words, now instead of writing path difference, we write the path difference as actually d sine theta. So for constructive indifference to happen, the path difference, which is d sine theta, must be equal to m lambda. And for destructive indifference to happen, the path difference, which is d sine theta, must be equal to m plus half lambda. Okay, so what I've done is basically to perform geometrical construction to describe interference pattern, all right, of constructive interference. The same can be used for destructive interference. The only thing will be for destructive interference, you just go to a dark spot, that's all.